Welcome back. Today we want to talk about what is the basic idea behind the Fourier transform and why did the founder, the Joseph Fourier, find this especially. Yeah. To start about that, let's just start about the things around us and how the world works generally. Generally, to analyze things, what do we do is that we see things around us by what we know already. We try to compare it and we try to measure or we try to say some units for it. Say for example, if you want to measure my height, we'll take a scale. Yes, obviously true. But the scale will have some units. The scale is also manufactured in a way that, okay, this is 1 meter. So I'm actually going to make this scale of this particular length. So it's a 1 meter scale. And you try to measure the height with the same scale, saying that it might be 1.5 meters, my height may be 1.5 or 1.8 or yeah. So you try to measure it and say that this is 1.8 meters. But what is meters? Right? So if you go deep into that, say that like meters is an SI unit, it's a standard international unit. And what do they say is that since the speed of light is 3 into 10 power 8 meter per second, the distance the light travels in vacuum for a fraction of 3 into 10 power 8 meters per second, like 1 by 3 into 10 power 8 meters per second, right? Like for a fraction of 1 by 3 into 10 power 8, for that fraction, how much ever distance the light travels, we call it as meters. So it's basically a fraction of time, and that time we tell it as 3 into 10 power 8, 1 by 3 into 10 power 8. So that we call it as meters. The same thing goes with time also, like the amount of time the cesium-133 atom takes its electrons to shift from one particular state to another state. We call it as 1 second. So we always compare it with something else. Here for length it is basically the speed of light, a fraction of the speed of light. And for time we call it as like for the electrons to transfer from one particular state to another particular state to a cesium-133 atom. But what I'm planning to stress here is that we always compare it with some other thing and say that with respect to this it is twice of that, with respect to that it is thrice of that. Probably we are putting a different name called as meter or second instead of each time saying it as okay, this is this much times the like the speed of light, or this is this much amount of time, or this much amount of length or distance of speed of light, or the states which the electrons moves. But we are not telling that in detail. We're just abstracting it and saying it as okay, this is seconds, and we're saying that this is meters. But that's the deep meaning it implies. So everything is relative. So relativity, like no, I'm not talking about relativity, but what I'm stressing is everything is relative. Whatever you're comparing and putting a unit to it. Yes. So that's the same thing Joseph Fourier also took. So he following those footsteps of taking things relative, because you have something in hand and you're trying to see that from that perspective. So he developed a tool called as Fourier transform or Fourier series. Fourier series is slightly different, but what I'm going to talk mostly about is Fourier transform. So what he took is he took sine wave. He just took a sine wave and told that whatever object or whatever signal you're gonna give me, I'm gonna see from the sine wave's perspective. I'm gonna see with respect to the sine wave, and I'm gonna say if it is a square signal, I'm gonna say that you need to add these many sine waves of this much frequency to get this square wave. So I will represent it with the help of some equation or some function which says that you add these many sine waves and you get this square wave. So he also took a relative approach. take this and see from that perspective. And this is very useful. This is very, very useful in a lot of context. First thing is that, like, if you see, like, it breaks down the having one single thing to represent a lot of different things, unifies the whole analysis. Yeah, it's a universal language. And the second thing is that what I want to stress is that about domain. Since he took a sine wave, like, since the sine wave has a positive side and a negative side, what happens is that it has a frequency, so it changes its value from a positive amplitude to a negative amplitude. So it changes its phase, plus 180 degrees and minus 180 degrees. So it changes its phase. So because of this, what happens is that, like, you can represent a variety of signals, not just not just a single kind of an approach. So things, whatever you see around you, change with time, right? Yeah, like the rate at which I'm speaking, or whatever, like the video is taking has this many frames per second. Everything is changing with time. But say, for example, if I have an object in my hand, which is just stationary with me, it's just staying in my hand. Like, although that object moves along with Earth, because we all are moving at the same speed of Earth, but relative to me, that object is stationary. Like it's so difficult to represent it. Okay. Yeah. This is where I actually would like to bring a quote from none other than Nicholas Tesla. So what he says is that, like, if you want to understand the world truly, think about it in the form of energy. Think about it in the form of energy and frequency. Yes. So it's a very good way to represent things. Very good way to understand things. Say for example, if I have a stationary object in time domain, if I want to use it for analysis, I have no other way to just put it as 0. It's static, right? But if you take it in frequency domain, right, then I can interpret more attributes to it, or I can interpret more parameters to it. Say, for example, I can bring in the concept of space. Say, for example, if I am having that object here, I can tell that it is this much height from the ground, so I can bring in the potential there, energy related to it, how much energy it stores, or how much energy it inherently has inside it because of its configuration, because of the material it has. So, or what energy it vibrates with. So all the objects have a resonant frequency, so it always vibrates. So I can bring the concept of energy and frequency so easily to it, because energy changes constantly or fluctuates, right? So I can easily bring the concept and idea of energy and frequency to analyze the object a lot better, not just based on changes, but on the properties of it, or what it is made up of, or how it is placed and its configuration. So it opens a lot more new dimension of it. That's a huge added plus point for it. Actually, the way Joseph Fourier found it is, he was trying to solve heat equations, and he found that, like, to bring in the concept of energy and frequency of each object, and he was easily able to analyze the heat equation of heat waves. That's a huge added advantage of this method. So he brought a sine wave and he tried to speak everything related to the form of sine wave. And the third thing which is important of this analysis is that, say for example, if you want to represent something in time domain, right? Say for example, like if I want to see the changes in time domain, say for example, if I want to represent an energy storage element or some random element that changes with time, I need to differentiate it. So and based on how many elements that change, if I have 3-4 elements, then I actually need to differentiate it 4 times. We call it as fourth order differentiation, and as the order of differentiation increases, it becomes very difficult to calculate it. But if you bring the same thing, if you change it from time domain to frequency domain in the form of the energy and the form of frequency, it becomes so easy. Instead of following a complex differentiation action, you can just easily do a multiplication, because you are just multiplying these 2 signals and then getting a third signal. So like instead of seeing but in differentiation you will be seeing the small changes, the infinitesimal changes between these 2 points. Oh, from this point to this point, this has changed by this much. Oh, like I have to differentiate it. So these 4 things change at this particular rate or this particular order. So I need a 4th order differentiation or 5th order differentiation. But here you just need to have, you can represent anything with a form of a sine wave of different frequencies. You say that like the same small change, you can represent it by saying that it is this particular fraction of the sine wave. So it basically tries to bring the algebraic flavor to your analysis. So you no longer do a complex operation of differentiation. You just try to do an algebraic operation. You just try to add, multiply, add, subtract. So bringing an algebraic flavor to it reduces the complexity of the way it gets represented and the way it gets computed, the way we see it and the way we perceive it also. It becomes a lot easier. So that's how Joseph Fourier gave it. So that's the basis of it. So sine wave is the basis of Fourier transform, and we see it from that perspective. And since we are going to represent everything in the form of sine wave, it gives an algebraic flavor, and you're able to represent everything in the form of frequencies, energies, and that is a very powerful tool when you go deeper and deeper to smaller scales, because at smaller scales you don't know whether it's a particular wave, and this is a very powerful technique for scientific analysis. Thank you.